This shouldn't work, but it does, every single foggy morning. High on Mount Boutmezguida, in one of Morocco's driest mountain ranges, water starts dripping from an ordinary-looking fence. No motor, no pump, no pipe carrying it uphill, just wire mesh standing in the wind, quietly filling a tank below it. Rain is scarce here, making this one of the driest regions in Morocco. So where is all this water actually coming from? And if a plain fence can pull it off, why isn't every dry mountain on Earth covered in them? The answer isn't buried underground. It's floating in the fog, waiting for the right engineering to catch it. From a distance, this structure, called CloudFisher, looks disappointingly simple. Steel frames, stretched netting, nothing more. But it isn't a filter, and it isn't pulling moisture from dry air with some hidden machine. It runs on physics that happens overhead every day. For roughly half the year, cool Atlantic air rises against these slopes and turns to fog, thick enough to see, light enough to drift on the wind. Engineers position the mesh directly in its path. Wind does the delivering, the net does the catching. But fog drifts over dry regions all over the planet, so why does this only work here? Here's the first surprise. Fog isn't water vapor. It's made of billions of tiny liquid water droplets suspended in the air. So small they don't fall, they float. As wind pushes that floating water through the mesh, the droplets collide with the fine fibers and stick instead of passing through. They merge. Once a bead is heavy enough, gravity takes over, and it runs down the fiber like rain on a window. It looks like the fence is making water from nothing. It's really just catching what was already there, and catching it turns out to be the easy part. Why doesn't the wind destroy it? Earlier fog nets used flat plastic sheets, and flat sheets behave like sails. In early projects across Africa, including a flat net system the Water Foundation ran in Eritrea back in 2007, mountain gusts routinely bent frames, snapped cables, and tore the fabric apart. Large-scale fog harvesting stayed a niche idea for years because of exactly this weakness. German industrial designer Peter Trautwein, working with the Water Foundation and his company, Aqualonis, argued the concept hadn't failed. The shape had. Instead of a flat sheet, he built a three-dimensional mesh, suspended loosely inside a steel frame on rubber expanders, so the structure could flex with a gust instead of resisting it. Field testing showed the redesigned mesh could withstand winds of up to about 120 kilometers an hour without tearing. If a fence engineered to survive winds of around 120 kilometers an hour sounds surprising, wait until you hear what's actually inside the mesh, because the real secret isn't the frame, it's the fabric. Subscribe now, and let's get into it. Stretch almost any net in the fog, and it'll catch a few drops. That's nowhere near enough for a village. The gap between fibers has to be exact. Too wide, and droplets slip straight through. Too narrow, and the wind slows before it ever reaches the mesh, so less fog arrives to begin with. During a 2-year field trial on Boutmezguida, Aqualonis tested 10 fabrics before settling on a 3-dimensional spacer mesh made from a specially developed food-safe monofilament polymer, engineered to withstand extreme UV exposure without breaking down or contaminating the water passing over it. And here's the twist. The breakthrough wasn't building a stronger fence, it was redesigning the tiny fibers that almost nobody notices. How the water reaches the villages. Catching the water was only half the job. Getting it down the mountain was the other half. On this site, every gutter beneath the mesh feeds into buried pipelines, running downhill on gravity alone, no pump, generator, or electricity anywhere in the system. Engineers buried the line to protect it from sun and heat, keeping the water cooler in storage. It's a simple trick with an old logic behind it. Let the mountain do the pushing. At Boutmezguida, that gravity-fed network reaches 14 surrounding villages and a school on the slopes below. Before the nets went up, Women and girls here spent hours every day walking to distant wells just to fill a jerry can. Once the pipeline connected their homes, that changed. The project now gives around 1,150 villagers up to 18 liters of clean water per person per day, more than double the 8 liters they had before. How much water, really? So how much water does one installation produce? It changes by the day. Fog density, wind speed, mesh size, even the ridge's shape all affect the yield. Depending on the region and time of year, CloudFisher can typically harvest between 10 and 22 liters of water per square meter of mesh, with a recorded peak near 66 liters per square meter on Bau Mesguida. That site now has 31 collectors installed, covering roughly 1,700 square meters of mesh. On a strong fog day, the full array can produce up to 37,000 liters, enough to supply the 14 villages and one school now connected to it. Some mornings deliver only a trickle, others fill the tanks fast. The system was never built to guarantee a fixed amount. It was built to reliably catch water that would otherwise just drift past. Why every desert doesn't have one? So why hasn't this solved water scarcity everywhere? Because fog harvesting doesn't need dry air. It needs wet fog, and that's rarer than it sounds. Bau Mesguida works because moist Atlantic air is forced upward against the mountain almost daily for half the year, condensing into low cloud right at collector height. Move the same mesh into a hot inland desert with clear skies, and almost nothing happens because there's no fog to catch. Bau Mesguida sits under fog around 140 foggy days a year, at an altitude high enough to sit directly inside the cloud layer instead of beneath it. A fairly specific combination of coastline, elevation, and wind that most deserts simply don't have. That's why researchers call fog harvesting a site-specific solution, not a replacement for wells or desalination. But where that combination does exist, the mountain is already doing most of the work. The engineering just had to stop getting in the way. Real projects around the world. Once the Morocco design proved itself, similar collectors followed elsewhere, each tuned to its own terrain. On Chile's Atacama coast, researchers were testing fog nets on this same principle decades earlier, drawing on the region's Camanchaca sea fog. In Eritrea's highlands, the Water Foundation and FogQuest installed simple flat net collectors back in 2007, above 2,000 meters, in the villages of Nefiset and Arbor-Obu, an earlier version of the idea, before this flexible 3D mesh existed. In Tanzania, Aqualonis has upgraded fog collectors at a secondary school in Kameyu, more than 2 kilometers up on a highland plateau where wells aren't possible, replacing older nets that kept tearing in the wind. Back at Bau Mesguida, the installation remains the largest operational fog harvesting park in the world, still supplying those same 14 villages that once shared a handful of failing wells. None of these projects mean a country runs on fog alone. Each one is a single site, matched to a single mountain and a single wind pattern. Engineering improvements and what's next. The design keeps changing because the fog does too. Researchers are testing multi-layer mesh that adds more collision points for droplets without slowing the airflow that carries them in. Others are working on coatings that shed dust faster, since a caked mesh catches almost nothing. Maintenance stays deliberately simple too. On the current design, the rubber expanders that hold the mesh in place are the only part likely to wear out in a storm, and they're cheap enough to replace without flying in outside engineers. And there's a harder problem ahead. As regional weather shifts, some fog belts are producing smaller, more scattered droplets, harder for any net to catch. Engineers are running new fiber geometries through wind tunnel testing in Munich to try to stay ahead of that shift. But the goal isn't to reinvent the concept. It's to keep refining one working idea, fiber by fiber. So a mesh that already runs without electricity, pumps, or moving parts keeps working as the fog itself changes. Conclusion. So, back to the fence on the mountain. It was never making water out of nothing. The water was already there, riding the fog, drifting past unused. The real breakthrough wasn't finding a new source of water. It was realizing the water had been there all along, and building something simple enough to catch it, without a single moving part. Wind carries the droplets in. Fiber gives them somewhere to land. Gravity does the rest, all the way down to a tap in a village that once had none. No motor, no pump, no mystery left once you know where to look. Somewhere on that mountain, another morning's fog is rolling in, and by evening, a family that once walked hours for water will simply turn on a tap. Just a fence, standing in the fog, doing exactly what an ordinary object was never supposed to be able to do.